So this is lecture 4, and we're going to start talking today about our second method. We're going to learn the course, and that second method is KNN regression. So let me write that down. KNN regression. So this course is a bit topicsy in that we're going to learn a bunch of different methods in this course. So the first method was regression, and the second method that we're learning is KNN regression. And so we're going to learn some methods. We're then kind of periodically going to go back and talk about how these things are related. But first, we kind of need to build up some methods before we talk about how the methods are related. And rather than starting with a whole bunch of dry theory, kind of unmotivated, having never seen any real method, I think we should first talk about some real methods, and then we can talk kind of theoretically what the underpinning of these methods are and what the relationships are between these. So our second method is KNN regression, and not surprisingly, this is a regression technique. That is, it's a technique for predicting continuous outcomes y. So as I said before, the word regression in kind of a machine learning or statistical learning framework, more broadly than just linear regression, means any kind of problem where we're predicting a continuous outcome. So linear regression, or least squares linear regression, is the first technique, and KNN regression is another technique that tries to solve the same set of problems. Here, KNN stands for K nearest neighbors. And K is going to be a parameter. So you also sometimes hear this just as a nearest neighbors regression. But people typically use the parameter K for the number of neighbors, which we'll see in the approach. And so it's typically called KNN. So if we think back to our setup for these learning problems is that we have some set of training data. And our training data is some y's and their associated features, x. These y's are some continuous number, some real number. And these x's kind of generically are in some p-dimensional space. And we assume that these are related. That is, that we can predict the y's from the x's, or there's some true underlying relationship where kind of generically y is approximately some function of the x's. So here my capital Y and my capital X are just generic y's and x's, right? Maybe I could write it's f of x1, x2, all the way up to xp. And the first technique, before we talk about KNN regression, the first thing we had looked at was linear regression. And linear regression makes a certain assumption about the form of f. So it makes the assumption about f that it is linear. So here, what linear regression basically says is that if y is f of my x's, that this f takes a particular form. And the form f takes is some intercept term, and then it's the sum of some coefficients, some beta j's, times my x's. So it makes this linearity assumption. In kind of if we just had one x. So if p were equal to 1, we can obviously draw this relationship. And so my intercept would be beta naught, and I would have some linear, that's supposed to be a line here, some linear relationship. The slope of this is going to be whatever beta 1 is. So if this were x1 and we're plotting y against x1, this would be f of x1, right? And so this is a very strong global assumption about f, because it says that f is linear with slope beta 1 everywhere. So when I say global, I mean that it's making this assumption everywhere. The relationship is always linear. So it's this kind of very strong assumption that over the entire space of x's, the relationship between y and the x's is linear. And that linear assumption does some work for us. The work it does is that it reduces the problem from an infinite dimensional space of all possible f's to a p-dimensional space where all we need to do is determine the coefficients for this linear form. So let me say what this does for us is reduce dimension of the problem from, if you recall back to that first lecture, I'd use maybe a script f for the set of all possible functions. It reduces it from f being an infinite dimensional space to the search space of possible f's, in this case having p plus 1 dimensions. P plus 1 because we have an intercept beta naught. So to contrast with linear regression, we're going to talk about KNN regression. And in contrast with this strong global assumption that linear regression makes, this is going to make a weaker, fairly weak, local assumption about the relationship between, how do you spell between the x's and y. So let's look at an example of how KNN regression works. And I think that this local assumption, what I mean by this, will become evident. Basically, it's going to say that the relationship between the x's and y's is, we're only going to make smaller kind of local assumptions about what this relationship looks like. It's not going to make a huge assumption that the relationship between the x and y is always linear and always has this intercept beta naught and always has the slope beta 1. So let's imagine that I have some training data. So my training data consists of pairs of x's and y's. And so my training data, maybe my training data looks something like this. How many points do we want? I don't actually want too many points. Otherwise, it becomes annoying to draw. So let's say that's our training data. So here are here's x1, y1. Maybe this is x2, y2. This is x3 and y3. This is x4 and y4 should be up there. x5. 5, And maybe we should make this point slightly different. So let's put y6 up here and x6 all the way over there. That x5 is not really centered, is it? Right? Oh, maybe it is. Something like that. So in contrast to linear regression, what KNN is going to try and do is it's going to try to follow, kind of only make restrictive assumptions, not about the whole global space, but about locally what's happened. So let's assume in our case that k is 3. So k here is a parameter. We are free to choose, and it's some integer. It's going to be the number of neighbors we look at. So if I have a new point, and I'm going to put my new point here, let me call it x naught. And I want to predict at this point x naught the value of the corresponding y that should correspond. So we think it should be somewhere around here. If I were to do this in linear regression, so to come up here and say, here's my x naught, this would be pretty easy. What we do is we go up to the line, we'd say, okay, whatever point is on that line, that's my y naught hat. It's my predicted value of y for the given x naught. For KNN, we're going to choose a certain number of neighbors, and we're going to say which of the neighboring x's in my training data. So again, these green x's are training data. And it's going to say which of these x's are closest to x naught. So in this case, it looks like x3 is pretty close, x2 is pretty close, and then I don't know if x4, x1. Let's assume that x1 is closer to x naught than x4. So all I'm going to do is basically calculate the distance of x naught to all the other training data, x1, x2, x3, x4, x5, x6. And I'm going to say, what are my nearest neighbors? My k nearest neighbors. So these 3 points are my k is equal to 3 nearest neighbors. And hence the name of the algorithm. And I'm going to say that the predicted value corresponding to a value of x naught should basically just be the average of the corresponding y's. So x1 corresponds to this green y1. x2 corresponds to that one, which we said is y2. And x3 corresponds to this one, y3. And if I average the y's, just kind of eyeballing it, it's going to be somewhere about here, maybe? Somewhere about here. And so my predicted value for y naught, I'm going to put over here. This is what I'm going to call y naught hat, my predicted value. That's the entire algorithm. Thanks for coming to my TED Talk. So this is the KNN algorithm. All we're going to do is we're going to pick a number of neighbors, and if I want to predict at some point, I'm going to find the training data points that are nearest to my x, and then I'm going to predict the average of the corresponding y values for as my predicted value. And so what this is doing is it's making a local assumption about the functional relationship. It's saying that I don't need to think about the points way over here, these x4, 5, and 6. They're not near x naught. It seems reasonable that if the x's that are nearest, if there's some real relationship, as we wrote, between y and the x's, then it seems like if I want to predict the value of y that's going to be associated with some x naught, the value of y that's going to be associated with x naught should be close-ish to the values of the y's that are associated with the x's that are close to it. So if we pick things that are similar to x naught, we're basically assuming that the y naught hat is going to be similar to the corresponding things that are close, the corresponding y's to the things that are close to x naught. So this is basically some kind of local assumption about the functional relationship, is that locally things are similar. That we don't have to care about points that are far away, but locally the value of y of my function should be kind of an average of the things I see. So you can think of it as it has some neighborhood here around x naught, call it the k neighborhood, because it's the k closest points, and it's basically saying I'm only going to pay attention to points in this neighborhood and then kind of average things there. We could do this for other points. If I were to pick a point here, let's call it x naught star. So here's some other x naught. I want to predict the value of y associated with that x naught. In this case, I'm going to choose x, 4, 5, and 6. I'm going to average their values and or average the values of their associated y's. So basically, I'm going to pick x, 4, 5, and 6, which is these 3 points here. I'm going to average their values. Oh, it's probably somewhere around here, isn't it? That line up, maybe it should be about there, right? And we could do this for all of our points. If I did this for every possible point on my x-axis, theoretically, you would get some fit. And maybe it would go something like this. I guess I should go through the points that I drew there. Maybe it would look like that. And so you see that so this black line is basically, I'm assuming I've done this game for every possible point on my x-axis. And I'm going to get a different predicted value depending on where I am, depending on what's nearby, what the k nearest neighbors are to my putative point. I'm going to be averaging different y's depending on where I am, so I'll get different values, and I'll draw, kind of scribe out some line. And KNN regression, you can imagine the kind of predictor, the f hat, this is basically going to be f hat. And for each value I want to predict at, f hat of x, I kind of would go up correspondingly on the line there. So notice here that KNN regression is not drawing a line, right? It changes. The relationship changes. The slope changes. In fact, it's not really linear anywhere. So this is what I'm talking about by saying that it makes local assumptions, right? Locally, it has this kind of shape, this kind of shape here, nearby these points, but over here it has this different kind of shape over here, and it can kind of locally adapt to where it is because the value of f hat only depends on the kind of nearby points in the neighborhood of the x at which I want to predict. So this is when I say KNN makes a weaker local assumption. That's what I mean. We only need to consider the nearest points in the neighborhood. Whereas regression makes this kind of more global assumption. And it says everything's linear everywhere. KNN regression says, I'm just going to kind of say things that are nearby each other should be similar, which seems reasonable. And we'll see in this course, neither of these algorithms is better than the other, but some work better in some situations than others. And so that's one of the things that we're going to talk about over the course and try to help give some kind of intuition about when I would choose one of these over the other. Okay. So I'm a statistician. I have to write math every couple minutes, otherwise I get nervous. So you could write this out mathematically. Honestly, the pictures and description are the best way to learn KNN. But one way to think about it is that y hat, which is f hat of x, is going to be, right, so for linear regression, f hat was beta hat beta naught hat plus, the sum of the beta hats times the x's, etc. For KNN, f hat at some value x, above I was using x naught, let's just call it x, is the average of our k nearest neighbors. So this is a bit cumbersome to write out mathematically, but the idea is it is the average of certain yi's. So yi's are certain training points. And it's the average over which training points? It's the average over the nearest neighbors. How can I spell neighbors? To x, to the value at which we want to predict this x. You could write down mathematically, you would index, it would be all the i's such that I is in the k neighborhood of x. So that's how I would write it mathematically. This would be read, this is basically the k nearest neighbors, the k, let me write that, the k nearest neighbors to x. So you'll see this written sometimes. It's a little cumbersome to actually denote the set over which we sum, but it's basically, we're summing over, and that's actually wrong. Good thing I caught that. We're summing the yi's over the set of i's such that the corresponding xi is one of the k nearest neighbors to x, right? So you see why this is a bit cumbersome to write out. Really, all it is you average the y's that correspond to the k nearest x's to k nearest training x's to x I want to predict. But you could write it this way: the average of the y sub i's, my training data, my training y's, where I ranges over all the I, where the corresponding x sub I is one of the k nearest x sub I to x. And it's a bit cumbersome, right? You can do this so in our example here, this is a one-dimensional problem where I had one x and then I had a bunch of y's, right? But you can do this for training data that is p-dimensional. We just use the Euclidean distance to determine quote closeness. And there are, as you might imagine, many variations on this algorithm. We might talk about some kind of later in the course, or you can switch up other kind of distances, maybe not Euclidean. So basically the neighborhood, the k neighborhood of a point x is going to be the what? It's the xn, our training data points, such that how do we even write this out? This is really cumbersome to write, but yeah, let's not even write it out. That's going to be a real pain to write out. So let me just say that you determine closeness. I mean, practically the way you determine it is you use you write an algorithm to search through your points and find the closest ones. But if you have, and obviously if you just have a one-dimensional training x's, you just look at the difference between them, or the absolute value difference. But you can also look at you could look at this Euclidean distance, right, between the points to determine closeness. And notice that the algorithm stays the same because the y's are always just one-dimensional. The y's are just numbers, and so you're always just taking the normal average of y's. And the x's could be multidimensional. You could have many features. All you need to do is have some metric of closeness. So for numeric data, we just typically use whatever points are kind of closest in a Euclidean sense. So you can try and draw a picture here. This gets a bit tough because you have to draw a three-dimensional picture on a two-dimensional page. but maybe this is my plane, x and x1, x2 against y, and I would have some training points in this space. Then if I had some point x naught I want to predict at, I would just kind of look at the kind of Euclidean distance in the x space. I would look at kind of the Euclidean distance of these points kind of projected down onto the x1, x2 axis. And I guess this point here would, well, this point x naught is in this x1, x2 axis, and we kind of look at which points in here are closest in the Euclidean sense. So when I say Euclidean, I mean that. But it's the same thing. The y's are always one-dimensional, so we're good. So there is this tuning parameter that is kind of built into the name of KNN, which is K. So we could say, what about K? What happens as they change this value of K? So let's maybe look at an example. And need some training data. Let's say my training data are these green points. Let's do something simple pattern like this. So these are my training data points. And they have their corresponding y's. I'm not even going to write what the y's are. It doesn't really matter. And let's draw a couple different values of k. So maybe we'll look at what happens when k is equal to 1. What happens when k is equal to, I don't know, 3. And we have 1, 2, 3, 4, 5 training points. Let's look at what happens when k is equal to 5. So when k is equal to 1, what does that mean for my algorithm? So let's go back up to have this picture of how this algorithm works, right? Ultimately, what I'm doing is I'm going to choose the k nearest neighbor. So k is equal to 1. I'm going to choose the 1 nearest neighbor. That is the singular nearest neighbor, period, right? And I'm going to average the value, the y's of these k nearest neighbors. Of course, if I only have one thing I'm averaging, it's just whatever the value is. So if I run this with k is equal to 1, what's going to happen is that I'm going to kind of draw out what f hat would look like. If I'm in kind of closest to x1 here, so if I had a point here, x1, my value is just going to be x1. The closest neighbor is x1, and so the value I'm going to predict is whatever the y value for x1 is, so it's at this level. And that's going to be true kind of everywhere near x1. So as I kind of move left to right, it's going to be true until I get to a point. At some point, I'm going to be closer to x2 than I am x1. So I'm going to kind of move along here. At some point, I'm going to be closer to x2. When I become closer to x2, now my nearest neighbor at a corresponding x is going to be x2. And so instead of predicting x1, I'll jump up to x2. And I'll predict x2 kind of correspondingly all in that neighborhood of x2 until I move to a point where I'm closest to x3. At that point, my nearest neighbor will be x3. And so I'm going to say my predicted value is whatever the value of my nearest neighbor is, or the average value of my one nearest neighbor is, and I'll jump up and I'll start predicting at x3. And so you can see what's going to happen. We're going to get this step function. And then at some point, I'll be closer to x4, and I'll predict x4 until I get closer to x5, and I'll predict x5, and that goes out to kind of to infinity. So this is what my k is equal to 1 algorithm is going to look like. It's basically going to be the step function where we're going to predict just whatever the value of the training point, right? These green points are the training point. The value of the training point of whatever my closest training point is at each of my points. So this is f hat, where k is equal to 1. Let's go to the totally opposite end of the spectrum. What if k is equal to 5? Well, if k is equal to 5, at any point, as I move back and forth along my x-axis, I'm going to take the average of my 5 nearest neighbors. Well, it doesn't matter where I am. I only have 5 training points. And so no matter where I am, the 5 closest training points are going to be all of the training points. And so my average of these 5 closest training points will never change. So there's going to be some average, and it looks like it's somewhere about here, maybe. This is kind of the average of the y positions of my green training points. No matter where I am, if I'm over here, the average of my 5 nearest neighbors is just the average of the kind of y1 to y5. And no matter where I am, I'm going to get the same value. And so my KNN function, my f hat, given to me by KNN, is just going to be flat. Everywhere has the same set of neighbors, and therefore I'm going to get the same predicted function. So when k is equal to 1, I'm going to end up interpolating my data. I'm going to absolutely go through every single point, every training point. And when k is equal to 5, I'm just going to say anywhere. I'm going to predict. I'm going to just predict the. I'm going to predict the average of all my training y's. If k is equal to 3, we're going to get some behavior in between. It will change, but it's not going to absolutely go through every single point. It's not going to interpolate the data. It's not going to be constant. Hopefully, it will be some kind of smoother thing that follows the data better. Now, this is optimistic. In this case, it's not actually what you're going to get, but the ideal is that you're going to get something nicer that behaves somewhat in between, where it's not constant, but it doesn't interpolate the data. We'll talk about why that is, quote, nicer. But the general rule is that this parameter k in KNN controls what we're going to call the flexibility. That's supposed to be y. Flexibility of the method. And by flexibility, I mean how complicated of a shape it can create. So let me write this explicitly. High values of k, as we saw here, when k is equal to the number of training points, we have a very inflexible method. And low values of k, like when I have k is equal to 1, we're going to have a very flexible method. So if I have a low value k, I can fit something complicated. I can do all these jumps. I can basically perfectly interpolate my data. When I have a high value k, I'm just going to fit a straight line. Not a very complicated fit. And in between, we're going to have various degrees of flexibility. But the parameter k is basically going to determine what the amount of flexibility I have in my method. So in some ways, unlike linear regression, we'll talk a little more about how we can get more flexibility out of linear regression. Well, let's talk about that now. So let's talk about this as compared to linear regression. Compared to linear regression. So in some ways, this KNN method is more flexible. It definitely seems more flexible than linear regression. It doesn't make a linearity assumption. It can fit these trends that are non-linear, right? For some values of k, it can. Although for other values of k, it's much, much, much less flexible. It's much simpler. For a high value of k, when k is equal to the number of training points, it's just going to fit a flat line. So KNN has a huge amount of flexibility. So let's look at these two different approaches we've learned so far. So for linear regression, I want to look at the number of parameters that I need to fit. So that's a kind of a measure of flexibility. The more parameters I have in my model, the more options I have, the more flexible of an approach I have. So for regression, I have basically p or p plus 1. If you include an intercept, it would be p plus 1. For KNN, there's an interesting question about how many parameters does my model have. We didn't parameterize it in terms of beta or anything like that. The answer is basically we have n over k parameters in some sense. So n being the number of training points and k being the number of neighbors I use. So properly, I will get yelled at by the computer scientists if I don't point this out properly. What we're saying here is that something called the VC dimension, VC standing for some Russian names I can't pronounce, the VC dimension is n over k. So there's this kind of computer science-y statistical learning concept called VC dimension, right? So for an algorithm like KNN, you don't really have parameters per se, so you can't really count. Like in regression, I have beta 0, beta 1, beta 2, so it's easy to count them. For KNN, you don't really have those parameters count. Nonetheless, you can. There's a theory called VC theory, and you can come up with kind of a dimensionality of the space, of the functional space over which you search, right? So what I said about regression is that it reduces the functional space we search over from potentially infinite dimensional to a p or p plus 1 dimensional space. For KNN, effectively you're reducing it from potentially an infinite dimensional space to a n over k dimensional space. So n over k makes a little bit of sense, it has some intuition, because it's basically saying if I have n training points, and for each, and I'm using k neighbors, on average, I will break this space up into n over k bins, right? So you could think of, for each of these, like in the step function here, I need one value to parameterize the value of the step function here, one value here, one value here, one value here, one value here, right, for each of the different steps to tell me what value I need to predict there. So if k is equal to 1, I would have n parameters, one value for each of my training points. If k is equal to n, I would have one parameter. All I need to do is the one parameter to tell me where to put this straight line, that red straight line. Okay, so it's somewhat believable. And so this is called the VC dimension, whatever. It basically, on average, we need to have n over k parameters for KNN. So you notice here that as k increases, the flexibility decreases. Because if I have more parameters, I can fit a more complicated function. Parameters basically say, tell us a function, predict this value here and this value here, right? One parameter predict the value here, one parameter predict the value here, one parameter predict the value there, right? So more parameters means a more flexible method, means a more complicated f hat I can fit. So as k increases, since k is in the denominator, we get a less flexible method. As n over k goes down, my flexibility, my quote number of parameters, VC dimension, decreases. And conversely, if I look at a very low value of k, my flexibility goes up. Again, we saw when k is equal to 1, we had a super interpolating flexible fit. When k was n, number of training points, I had a really inflexible fit. It was just some straight line at y bar. So for KNN, this parameter k determines the flexibility. Notice that for regression, you can actually increase the flexibility. And one way you could increase the flexibility is you could increase the number of the value of p. Well, how can you increase the value of p, right? Isn't p the number of variables? P is not the number of variables. P is the number of columns in my design matrix, or p plus 1 is the number of columns in my design matrix, right? What really controls the fit is the number of columns in my design matrix. So maybe I should really just say, in linear regression, the number of parameters I need to fit is just the number of p, which is the number of columns in my design matrix. And how can I increase the number of columns in my design matrix? I could look at transformations of my variables. If including not only x1 and x2, but x1 times x2, how did we do that in the linear regression lecture? I added on a column to my design matrix. That was x1 times x2. And so I've increased that, and I've increased the flexibility, and I can, and not surprisingly, I have a more complicated model, and I can fit something more complicated. So both these methods have ways to kind of play around the flexibility. For regression, it's going to be increasing the number of kind of columns in my design matrix, or increasing the complexity of my design, as it were. For KNN, it's going to be choosing my value of k. Okay. So we got a little bit of time left, and so we've now introduced both KNN and linear regression, and we want to talk about evaluation. So evaluation basically being, how do I choose a method or parameters, right? We now have at least two different methods we can use to solve a regression problem. And both of these methods have different number of parameters, right? For KNN, I can choose the number of neighbors. For regression, I could change the number of variables, or add on complicated transformations of my variables, increase the value of p, and increase the flexibility of my method. And the question is, what's the best thing to do? So we want to talk about evaluation. How do we choose? Good methods? What's depending on kind of the data. So the first thing we want to do is define what a residual is. And the residual, let's call it E, is basically the predicted value minus the actual value. So this is predicted minus actual. And what we want in a method that, say, f hat, is that f hat of some x is approximately the y. F hat of x, of course, is what we're calling y hat. So we really want y and y hat to be close, i.e. small residual. In general, we want small residuals. And the question is, how do we have n training points, how do we summarize these residuals to give us a measurement of how good we're doing? So our setup, of course, is that we have our training data, which is what our y-ends, our x-ends, and we fit some f hat using our training data, using some approach, maybe regression, maybe KNN regression, and we want to evaluate if this f hat is good. So we can summarize the residuals in a couple of different ways. The easiest or most simple is I could form what is called the training residual sum of squares, which is called, I'm going to denote as RSS, residual sum of squares, and I'm going to say subscript train, because we're going to calculate on the training data, and RSS train is going to be just the sum of my squared residuals. So as the name say, it's the squares and summum of the residuals. The residual sum of squares, which is, of course, just the predicted yNs minus the true yNs squared, sum them up. That's probably the most basic way and to summarize things. You might have seen that in kind of like a regression class. And many of the other metrics that are out there that you might have seen are basically some one-to-one function of this. So another metric out there is called the mean. And we're going to specify here the training mean squared error, and this is typically denoted as MSE train. MSE train is going to be the mean squared error, or the mean of these things, which is basically just 1 over n times RSS. So some people don't like the fact that the RSS grows as the training data grows, so they could just look at the average instead of the sum of the squares. Other metrics out there, the so-called coefficient of determination, or R squared, and we're going to say training, so let's just say training, R squared. And training R squared, or R squared, is 1 minus RSS of the training over what's called TSS over the training. And so here, TSS train is the total sum of squares. TSS training is equal to the sum over my training data of the yNs minus y bar squared. So the yNs minus their average squared. Looks a lot like variance, pretty much is. So the idea behind R squared is that RSS is equal to how much variation is left in the data after f hat predicts. What do I mean by that? If you look at RSS, it's basically, I'm basically taking, you could switch these around and say it's yn minus yn hat. So it's basically, if I take yn and I remove the part that is predicted by f hat, how much is left over? And they look at the sum of squares, kind of the variance of those. So it's basically the variance or the variation left over after I remove y hat. TSS is basically the total amount of variation. So TSS looks almost exactly like a kind of sample variance. Right? In fact, if you like divide by n, it's basically a sample variance. And so the idea here is then that R squared is 1 minus RSS over TSS. RSS over TSS is going to be the percentage of variation, or the percentage of the total amount of variation. So the bottom is the total variation. The top is the variation that is left over after accounting for f hat, variation explained by f hat. And so RSS or TSS is it's a percent of total variation left or remaining after accounting for f hat. And so 1 minus that is going to be the percent of variation explained by f hat. So these are some metrics that we can use to evaluate our algorithms. We're gonna kind of stop here for now, but we can pick up on this thread next time, because now we've learned two methods, so we can start playing the fun games of comparing and contrasting them.